Hi everybody, this is Mr. Karlovsky. We're going to do day 2 of ellipses here with some applications or just some extension problems. And here we go for number 1. It says fully analyze this equation. Now obviously it's going to be an ellipse because that's the sheet we're on, but this equation does not fit in any of our forms that we are used to. So this is going to practice the algebra of turning it from this expanded form into the normal factored form with the structures where we can see our a and b value of an ellipse. So we're going to do some completing the square, and as usual, I'm going to bring my x squared or my x terms together. So 4x squared minus 8x. I'm going to get my 9y squared minus 54y. And then I'm also going to bring the 49 over to the right side and make that negative 49. All right, so now it's time to complete the square. I'm going to go a little fast here, factor out the 4. So I have x squared minus 2x. And then I need this to be a perfect square. Well, let's see, if I already have a minus 2x, I guess I could add a plus 1. But, all right, and I'll balance that out in a second. So that's what I added there. And then I'm going to have plus, I'm going to factor out the 9. Have y squared minus 6y, and then to complete this square, well, half of that squared would be 9. All right, so I've added a 1 and a 9, but no, I didn't. I didn't really add a 1, I really added a 4. So I have to balance out with a plus 4 on the right side. And here I added a 9. No, I didn't. I actually added an 81. All right, so we've now got 4 x minus 1 squared plus 9 y minus 3 squared equals, and then this right side, that's 85 and minus 50, and I think that's 36. Okay, now that definitely looks nicer, but remember our ellipse equation has to equal 1. So we're going to divide both sides by 36. Now we've made the numbers nice right now. I guess they won't always be nice, but usually they will be. So our equation is x minus 1 squared over, well now 4 over 36 is over 9, and then y minus 3 squared over, well 9 over 36 would be 4 equals 1. All right, so that's the algebra of changing it from that expanded form to the form where we can now have our a, b, and c. And now let's quickly do our analysis like we did last class. The center, of course, is at 1, 3. My a value is 3. My b value is 2. So if I were to sketch this, right, so 1, 3, and an a value in the x direction of 3, 1, 2, 3, 1, 2, 3, and then a b value of 2 in the y direction. So we have this little, almost football-looking guy here. It's supposed to be smooth. Oh, that's not great, but oh well. Make it look decent. All right, there's my sketch. All right, major axis length, double the A, 6. Minor axis length, double the B, 4. Where are the vertices? I'll do it like last time, where I've got my coordinate 1, and then plus or minus the A value of 3, 3. So that would be 4, 3, and negative 2, 3. Okay, so there's my major vertices. My minor vertices are 1, 3, plus or minus the b value of 2. And so that's 1, 5, and 1, 1. Okay, and finally the foci, which are more just for interest. Well, c squared equals a squared minus b squared. So c squared equals 5. So c equals the square root of 5. And yeah, they're not always perfect right triangle Pythagorean triples. So my foci in the x direction will be 1 plus or minus root 5, 3, and I'm actually okay just leaving it like that. Okay, so there's our analysis with the extra step of factoring at the beginning. Okay, let's move on to number 2. A really neat feature geometrically about an ellipse is a feature that physically anything that starts from one focus, if this is a physical world, would bounce off the ellipse and then go towards the other focus. Really neat physical feature, you're going to watch a video in a little bit about a pool table that use that for a game of pool. All right, so if you just read this real quick on your own about a medical procedure where, yeah, when you have to break up kidney stones inside someone's body, they put them in an elliptical tank, and then they create these shockwave pulses from a machine at one focus, and they line up your kidney stones inside your body at the other focus. And I think they put you in some like saline water to keep the consistency of your body all the way through. And and then they can break up a kidney stone inside your body, which seems kind of really dangerous and scary, but also really, really cool if it's effective. All right, so here's an example, excuse me, where it says, if the two foci are approximately 6 feet apart, that's how far apart the foci are, and the patient is located 1.5 feet from the edge. So I guess we're giving from here to the patient is 1.5 feet. And then the foci are 6 feet apart, it says. What are the dimensions of the tank? Now you might say, how do I give dimensions of an ellipse? Well, just kind of imagine it's a rectangle. So basically, what's the width and what's the height, or the length and the width? Or in our vocabulary, it's really the major axis and the minor axis. All right, so we don't have a coordinate system here, so I'm just going to assume it's centered at the origin. So I'm going to have x squared plus y squared equals 1, and we're going to fill in our two blanks here. Now, what are our ABCs? Well, let's see. Since the foci are 6 feet apart, that means C equals 3, right? Because it'll be 3 to one focus, 3 to the other. Now, the 1.5, that just tells us that from center to the edge along the major axis, well, that would be 1.5, so that would be 4.5. So that would be our A value of 4.5. Now, if we don't have to always simplify things, we could say, hey, now if I know our horizontal and my x squared is, or my A value is 4.5, I'm just going to write 4.5 squared. I don't need to figure out what that is exactly. And so now our typical, hey, let's find B, 3 squared equals 4.5 squared minus B squared. All right, this one we're going to need to figure out. And really, all I care about at the moment is what B squared is. And I go to my calculator and figure out what B squared is, which is 11.25. And so, as far as the equation, if I asked for the equation, I could just put 11.25. That's the B squared value. But I guess I do need to find what B is, and obviously not a nice number, square root of that, which is 3.354. And so I guess for the dimensions, now I could say, hey, what's the dimensions of this ellipse? Well, the major axis would be double the A value, so 9 feet. And the minor axis would be double the B value. And so what would that be? About 6.708 feet. All right. So neat little example of how an ellipse is used in the physical world. All right, moving on to one more problem. All right, this is not so much a application as it is just a way to understand our ABCs of an ellipse. So it says a bridge is built in the shape of a semi-ellipse. So physically that seems kind of weird. If I were to draw it, that would be like, so semi-ellipse, there you go. Now, I don't know if the bridge is the actual curve that we're driving over, or maybe this is more like a tunnel. I'm not sure it really matters, but a bridge is built in the shape of a semi-ellipse. The arch is 60 feet high in the center. So from the dead center to the highest part is 60 feet. And it is 160 feet wide at the bottom. From one end to the other is 160 feet. Find the height of the arch 25 feet from the center of the bridge. So find the height 25 feet from the center of the bridge. You got to read that carefully. And we're going to use our calculator to round to the nearest hundredth. All right, personally, I always like to just make these all coordinates. And if I have a semi-ellipse, I'm going to go ahead and let this dead center here on the ground be my 0, 0. Let's keep that a nice simple rectangular system. And if I do that, then that means the point up here at the top must be 0, 60. And then if this is 160 feet wide, then I could say that this point to the right here is 80, 0, right? Because if it's 80 to the right and 80 to the left. All right, so really now I've defined this ellipse. Now, it didn't tell us whether this was a wide ellipse, like a horizontal or a vertical one. They didn't have to tell us. The numbers tell us. So right now, I have the equation of my ellipse. It's clearly bigger in the horizontal direction than the vertical. So this must be 80 squared over under the x, and 60 squared under the y. So that would be the equation of the actual curve of the ellipse. And now the question says, hey, find the height, the y value, of the arch 25 feet from the center. So they're saying from the center, if I went 25 feet, what's the height? Well, think about that coordinate. That would be 25 for the x, and we're wanting to know the y. I like to just think about these 3 points. We've got the height, the width, and then a mystery point. And pretty much most of the problems we're going to see in this section, you're going to be kind of given 2 of those 3 points and then find one part of the third point. Okay, so yeah, so for us, we have x equals 25, so 25 squared over 80 squared, and we're going to solve for y. And you know what? You've got a calculator with a cast solve command, so why don't you just go ahead and solve that equation for y. And I got 56.995 for the y value, and so that's how tall the bridge is, or the tunnel is, at that moment. Right? It makes sense that it had to be less than 60, because 60 is the highest part. So yeah, so 56.995. All right, so I hope that'll be enough for you to get through the homework for tonight, which is just some more of these, applications of ellipses, or seeing them in the uglier form when it's all expanded and just manipulating it. But always remember, it comes down to your ABCs. This problem had nothing to do with the foci, so I guess the C was not important. But just, always kind of think about the structure of an ellipse with the equation. Where's the center? Where's the A, the B, and then if you need the C, find the C. All right. Well, good luck and have a good day.